Okay, good evening. We are starting another section of our study of neural networks. Neural networks are the central piece of today's revolution in artificial intelligence and machine learning. So it's worth spending more time on this topic. We have covered a few basic ideas already. We started with biological motivation of neural networks. Then we talked about feed-forward functions used in neural networks. Then we went on to talk about some simple methods of regularization of neural networks, such as a norm penalty, data augmentation, the tangent distance, and so on. And today we continue on this topic. You can think of convolutional neural networks as a topic in regularization. That's an interesting perspective. CNNs are quite famous today, that they're commonly used for all computer vision type of applications and used in other types of applications too. But why are there all these types of networks, ordinary deep networks, and why are there convolutional neural networks? You can think of it as another type of regularization. What kind of regularization is it? It is roughly the same as solving the problem of the inputs being subjected to transformations, right? We've been looking at that issue. That one could improve the performance of a neural network classifier by rotating and translating and scaling the inputs, and then feeding them to the network so that the network learns about all those possibilities and performs better than without using regularization. And we also saw that instead of simply creating more and more and more such transformed samples, we can somehow incorporate them into the network by using this idea called tangent distance, where we first of all learn somehow the manifold on which the data rests and draw a tangent to that. It's a little complicated matter, but we saw that there are some ways of computing the tangent, the derivative, and so on. Uh, so those issues are simplified when we move on to convolutional neural networks, abbreviated as CNNs. Here, we again are saying we would like to achieve invariance. And one way to achieve that invariance is by using the concept of convolution. How does that help? Normally, we go in a neural network layer to layer to layer, right? The convolutional neural network says instead of using a full layer with a full set of connections where you have to learn all of the weights from one layer to the next layer, you need to learn all the matrix, right? To go from one layer array of values to the next array of values, we need to multiply it by a matrix. Vector to vector, you can think of it as a vector multiplied by matrix gives a vector. Instead of a full matrix, which means you are dealing with all possible connections, the convolutional idea says, let us not take every input and multiply these values and give it to everyone at the next layer. Just focus on a small region around the input and use that repeatedly again throughout. So it says by focusing on a small region, you are going to be using only, and rest are all considered as zeros. You can think of it. So you are transmitting the value at 1 pixel, if it is an image, into some small region at the next layer. And so it is not going to be influencing something in far away on the far corners of the image and so on. It's just some local thing. So local operation, the convolution operation. So the reason here is that there is going to be dependencies in pixels locally. Okay, 1 pixel depends on the near neighbor, but it doesn't depend as much on a far off neighbor. So that is the intuition behind it. And why does that help is when you are rotating an image and so on, those local properties you're going to be extracting could also be somehow available in other parts too, but that is done by keeping the kind of weights you're going to multiply, repeat again and again all over. And say these kinds of local operations somehow may be valuable. Actually, when we go from layer to layer to layer with CNNs, we get local properties, and then the local properties allow you to create another layer where the local properties are aggregated. The next layer, again, the local properties aggregated. That way the influence passes along, and somehow the information in lower areas get influence in further areas at a later point of stage. So this was a clever idea of convolution that Jan LeCun, who shared the Turing Award, was for this concept of convolutional neural networks. So that's the topic of today's lecture. There is a lot to be said here. I'll see how much we can cover, and I presume you're already familiar with how to implement convolutional neural networks. And so that'll make it easier for me to go over this topic. So now before I begin, so I think I've given you a little bit of a motivation for convolutional neural networks. That is local weights. And also there is a concept of sharing of weights. Instead of learning the full matrix of weights that is going to be multiplying the input vector, we could say the weights are all kind of repeated all over. So it's called shared weights, the same weights. So the amount of computation needed is going to be lesser. So there is one thing is you're computing local features, and then you're doing fewer computations. So there are several advantages of this idea of convolution. So in order to study the convolution neural networks, we could begin in many ways. One is, first of all, learn what is meant by convolution. It's a mathematical operation. Convolution is defined for an input function. You can convolve it with another kernel function and get a new function as output. So we're going from one layer to the other. So if somehow we've got the input layer, it's some kind of a function of all these values, of all these coordinate values. We assign a value to each of them. And so we get another function after doing a convolution. And the convolution is defined like this. You have a function, and then you take a convolving function, and you kind of pass that function over all the values of the input function, and then compute the output values. It's like a little window you apply. If you think of a two-dimensional image as a function rather than a one-dimensional function, you're passing a kernel over all of it. And as you go along, you compute all the values with that kernel there. And then that's how you create a new output. So that particular thing that you're passing around is called a kernel function. So we need to be specifying a kernel to be able to convolve the input with a kernel. And then of course the kernel can be different. You can vary the kernel. Here is one kernel I pass around. Here is another kernel I pass around. That's going to create a different type of output. One kernel creates one type of output, another kernel causes a different type of output. One kernel could be for edge detection in the image. So somehow you're detecting the sharp transitions in the image. Another one could be blurring of the image in the kernel, or what have you. It could be left side edges, right side edges, upper edges, lower edges. So we can have several kernels and several convolved versions of the input. So that is quite typical to generate several convolved versions of the input. That is where the idea of tensors become useful. One two-dimensional image is becoming several two-dimensional images. All of them have been operated by a kernel. And now you work with all of, they're called channels now. They're channels into the network, and you are now processing all of them together. So this is the kind of adventure we get into in studying convolutional neural networks. So we again begin by the mathematical definition of a convolution. And then when you talk about CNN, there are some differences from the standard convolution of mathematics and so on. Okay, so let's, I'll share the screen. Okay, convolutional neural networks. So we will talk about the motivation. I think I've given you the motivation already. We'll look at the slides for that also. And what is the convolution operation in mathematics? And we'll talk about neural networks and matrix multiplications, how going from layer to layer is a matter of simply matrix multiplications. And then we'll talk about limitations of simple neural networks. Okay, so why was the CNN invented? Convolutional neural networks. And the concept of pooling, which commonly goes along with CNNs, and the architecture of a convolutional neural network, and the nature of backpropagation in a convolutional neural network, and advantages of CNN architectures. So, motivation for CNNs. So it's another approach to creating models that are invariant to certain transformations. So we've already talked about it. Other approaches are data augmentation, tangent distance. So it is another approach to make it invariant. That's how it started, invariant to certain transformations. That invariant means if I give you a 7 and I rotate but the 7 by a little bit to the left or right, the output should still be 7. Invariant means it doesn't get so dependent upon the particular orientation or the scale of the image or the position of the image on the screen. And CNNs have been widely applied to image data. Example, MNIST images subjected to translations, scalings, and small rotations. That's how it all began, by saying, how can we do digit recognition without having to provide as input so many variants of the input? Can we somehow make the network itself handle this issue of invariance rather than providing explicit data that is transformed? The CNN approach exploits the fact that nearby pixels are more strongly correlated than distant pixels. So extract local features that depend on only small subregions of the image. It says you should take into account the context in local areas. Information from such features can be merged in later processing stages in order to detect higher order features. So although we are focusing only on local features, it's not like we are forgetting that, that there might be some dependency in an image between the left extreme and the right extreme and so on. It's done at a later stage, at a higher level. So CNNs incorporate three mechanisms. Local receptive fields. I guess we use the word local receptive fields because the human eye, the biological eye, is also like that. And I know our eye also operates like that. It takes the light that falls on the retina, and the nervous system carries that information with the receptive field of these image pixels. Are going to be local, small region, maybe overlapping regions. That's how it is transformed, rather than all of them being brought in at the same time. And then the concept of subsampling is brought in here also. That subsampling is an older word. Convolutional neural networks have been around for a long time, and today we don't use the word subsampling in neural networks. It's called pooling, where we say instead of using the entire field, you somehow reduce it by a certain number. And say instead of 4 pixels, a square of 4, you use 1 pixel. That's called subsampling. So that subsampling could be, instead of those 4, use just one of those values. You get a lower resolution image. Another way of subsampling is to take the average of them, maximum of them, like so on. That subsampling idea. Weight sharing is the kernel values that you're going to be using is a it can be thought of as the weights that are being multiplied. And so that is what is being repeated again and again. That's called weight sharing. So you're not learning as many weights. This is a complicated looking slide. Main thing I wanted to convey here was what is the mathematical function of convolution. So convolution is a well-known mathematical operation. If I give you two functions f and g, then the convolution of f and g, they're both functions of an input t. So the convolution of the two functions is integral of minus infinity to plus infinity, f of t, f of tau actually, g of t minus tau d tau, right? So it is somehow two functions that are, we take the f function, the g function, t minus tau says, flip one of the functions. And at every point on the axis, you multiply the two values, and then you run over all the values of the, let's say, the tau axis or the x-axis, add them all up. That's what the integral would be. Here is an example of a convolution. F is, let's say, the input is this function. It's a function which is a pulse, right? A pulse function. It looks like a convolution is being used in the time domain here. That's a pulse. That's the kind of stuff that the biological neural network system does. It sends a pulse along the axon. And so that is, and then convolution, we have to choose a kernel. What is f function is the input function, g function is the kernel. Here's the kernel. What happens when you convolve f with g using this formula? This calls for flipping this g function the other way around, and then passing it from left to right and multiplying the corresponding values and adding them up. So this value f star g is the convolution, f star g. There's a property, f star g of t is equal to g star f of t. It's a symmetric operation. I mean, if I could flip f with respect to g, that's what he's saying. You can flip either g or you can flip f. So this is what the function is going to look like. That's interesting. This is what we're going to get out of this. And anyway, this diagram kind of tells you that. G star f also comes out looking like that. And this is all explanation of what is happening here. So you see here is the flipped version and this being superimposed. And we are moving it from left to right, and it's explaining to you why these values are coming out as they are. A little bit of a curve here, although there is no curve in these two. So this is what a convolution operation is. Let's say here is another one. Here is an input f of t. It's this function here that's starting at some high value and heading towards 0 here. That's the input function. It's a function of t, right? And the kernel we're choosing is something like that, which is g of t, which has got this shape. It's got it goes from 1 to 4, it drops off to 0. So when you flip that kernel, it's going to have this form. G of t minus tau is going to have this particular form, the flipping. And this flipped function is now passed from left to right from this function, like it's shown over here. And then you're going to multiply the corresponding values. That's what this calls for, multiplying the corresponding values, and you got to add them. Oh, I don't have the what it's going to look like. What does the convolution function look like? Okay, I think I got this out of Wikipedia. Take a look at the Wikipedia. Anyway, this is just the idea of what is meant by, this is a one-dimensional convolutional convolution. So that is where the idea of convolution comes from. And here is the discrete version of convolution. So if you have a function f of t, so t takes on the index value 1, 2, 3, 4, 5, 6, 7, 8. And the f of t has a value 0, 1, 2, minus 1, 1, minus. So it's some function of the input that has got some fluctuations going on here. And we happen to use a g t minus tau, that is the flipped kernel is 1, 0, minus 1. So when you do that, what happens? When we convolve the two. So we now have parameters of the convolution: kernel size f, padding p, stride s. So we have the f of t is being defined like this: 0, 1, 2, minus 1. Is that the same one? I wonder. Yeah, 0, 1, 2, minus 1, 1, minus 3, 0. Anyway, this is the FT. The function looks like this function. And we are convolving with this kernel here, 1, 0, minus 1. So when we apply that kernel 3 at a time and then keep moving it, so it multiplies 0 with 1, 1 with 0, 2 with minus 1, and add them up, right? That's going to give us a 0 here, a 0 here, and a minus 2. That's how we get the minus 2. And then we move it by 1 and then repeat, 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 repeat like that. So when we use this kernel with this function, we're going to get a f star GFT. It is this set here. And we are using what we say a stride of s equal to 1. So we are kind of moving it by 1 each time. That's the stride. So instead of moving it by a step of 1, we could also move it by a step of 2. And when we do that, we're getting a smaller output. Previously, we got a 5 pixel output, let's say. Input was a 7 pixel, and then the next one is 5 pixels. This one, when we have a stride equal to 2, we got only 3 values here. We also do what's called as padding here. Kernel size is f. The kernel size was 3. Padding is although the input was 1, 2, minus 1, 1, minus 3, we pad it with a 0 on the left and a 0 on the right. Similarly, 0 on the left, 0 on the right. That's called the padding. And then we got the stride. We just talked about what is meant by the stride. So in order to define convolution, you need a kernel and a kernel size, and you need a padding around the input, and then you need a stride to compute the convolution. So this is just as if the function was a one-dimensional function. We now have to imagine in a two-dimensional space, because the image is a two-dimensional vector rather than a two-dimensional matrix rather than a one-dimensional vector. So here is the two-dimensional convolution. So let's say the input was A, B, C, D, E, F, G, H, I, J, K, L. And the kernel was W, X, Y, Z. So we want to convolve. Was there a question?
Same.
All right, there is some ambient noise. All right. Okay. So we are convolving this input image A, B, C, D, E, F, G, H, I, J, K, L with a kernel W, X, Y, Z. And what are you going to get as output? So this would say W times A, X times B, E times Y, F times Z is this first value. And then if you use a stride of 1, we move it to the left, it becomes B times W, C times X, that's all these terms, F times Y and G times Z, and like that one more time when we move it. So on, of course, when we move it over here, we need a padding on the outside, because we get one value in this position, one value in this position, one value in that position. I guess they don't get the fourth value here. We could get the fourth one by putting zeros. So this is only 3 values here. So 4 values here became 3 here. And then 3 rows here become 2 rows here. So they didn't do the padding here. So this is 2D discrete convolution. So this is the idea of convolution, going from one-dimensional continuous function to discrete one-dimensional function to discrete two-dimensional function. So uses of 2D convolution. Here is an example. Here's an image, a black and white image, where the values are 0, 1, 2, like that. Take it as a grayscale values. And there is an input image, and we're convolving something 400000000 minus 4. And we are applying it on each cell and then moving like that. When we apply it on this leftmost, that gives you a value. This shows all the values. It's 4 times 0, 0 times 0, 0 times 0, like that. There is a minus 4 times 2 here. The total of all of these is minus 8. That's the value minus 8 that's coming out here. So by convolving it like this, you're going to create a new image. And it turns out that if you choose these kernel values carefully, you can do all kinds of interesting operations, like a kernel for blurring. So this is an image of the Taj Mahal here. And we have a kernel for blurring. Supposing we want this blur this image, then we would use a kernel like this, zeros, 1, 1, 1, 1 all over. It's kind of mixing up all the values. Kernel for edge detection. Supposing we want to figure out where are all the edges in this. And the kernel for edge detection would be something like 0, 1, 0, 1 minus 4, 1, 0, 1, 0. And you convolve it like this, the output is going to be an image that looks like this, which detects all the edges in the image. That's simple. So if you want just the edges to get a line drawing of that image, you can convolve it with this particular kernel, right? And here is another image. This is some Roman aqueduct image here, and it is being processed by this kernel. This is another image actually. I suppose it is something like this. -4 must be black, and in each of these directions, it is four cardinal directions. It is white, and the diagonals are 0, and you pass that and you get a line image of this aqueduct. And kernels for line detection. So this is for detecting lines in an image. This is for horizontal lines, -1, -1, -1, -1, -1, -1, 2, 2, 2, like that. And vertical lines can be detected using this. And this is, 45-degree line and 135-degree line. So you can have all these kernels. So you can process your image saying, get me the edges of it, get me the blurred version of it, get me lines in one direction, get me lines in other direction. So you can imagine this is going to be really useful for computer vision. The human eye and the biological eye, they actually perform by detecting edges where things change. That's what it's detecting. That's what the biological brain also does. Where are things changing? When a frog is looking at an insect, it doesn't detect it unless it moves. It's only detecting changes. That is how it detects things. So just like that, these edges are useful things. So you got a biological motivation coming in here. Isn't that interesting? We said the neural networks, we are constantly motivated by the biology of the brain. And we said neural network is somehow modeling the brain. By the way, I came across this. I was reading an article, just yesterday, uh, as to we already saw that the number of neurons in the human brain is what, 10 billion, right? Right. We started our discussion on neural networks saying how many neurons does the human brain have? 10 billion. But then if you ask the question, how many weights does our brain have? That's a different question. How many neurons would be how many in one layer, how many in the next layer, how many in the next layer? So you're counting that. But if you now talk about all the connections, may not be everything is connected to everything else, but whatever is connected to whatever. So how many connections are there in the brain? Or in other words, how many weights are used in the human brain? That turns out to be trillions. Is that something? Each of us have a trillion trillion weights in our head, which is what makes us reasonably smart, I suppose, right? Trillions. And then you ask the question, well, we got all kinds of smart computer programs that can drive a car or that can detect our face. How many weights there are in the most sophisticated machine learning program? And it turns out they're not of the order of several trillions. They're much, much smaller, much smaller, the number of weights. Isn't that fascinating that today's machine learning and AI does not have as many parameters as are in the human brain. So we can argue that why today's computers or today's AI machine learning is not as good as human beings is we haven't given it enough of a brain structure, right? And one can argue that all the sophisticated AI that one can think of is all done by these neurons and neural networks and these weights and things like that. So none of the other approaches, older approaches to AI are needed, so that it gets into a more forward-thinking discussion about the comparison of the human brain and the neural network. Anyway, I got carried away a little bit here. Let's get back to convolutional neural. Okay, the reason I brought it up was even not only the neural network, but also the idea that the human eye does edge detection. Well, that's what CNN does, convolutional neural network. Oh, wow. So that it's very exciting that we are kind of paralleling the biological works here when we talk about CNNs, because that is how the brain seems to work as well. This slide, okay, we don't get too carried away by the biological motivation, because we're trying to implement useful programs. And this slide is only telling you that when we go from one layer to the next layer to the next layer, all we are doing is matrix multiplications. I think I've given you this diagram before. We go from x1, x2, x3 to y1, y2, y3. How do we do that is by multiply by all these connections to the hidden layer, where we also are adding BIs to them. And some activation also has to be done to get the YIs. And so all of these values, we can label them as W11, W21, etc., can all be organized in terms of a matrix W. And so we can argue that that from the X's you get the Y's, or the Z's first, right? From the X's you get the Z's, from the Z's you get the Y's, right? So this should have been Z over here. Okay, so it can be written as a W transpose X plus B. So in a way, the X is a vector here, Y is a vector here, Z is a vector here, W is a matrix. And what is that matrix? These are all the values along the connections. And so this can be all done as matrix manipulation. All right, so that is that. So I've done two things now. Discussed convolution. I've discussed what the neural network does, going from layer to layer, matrix multiplications. So limitations of simple neural networks need substantial number of training samples, slow learning convergence times, inadequate parameter selections, techniques that lead to poor minima. Network should exhibit invariance to translation scaling and elastic deformations. A large training set can take care of this. Yes, you can do that kind of regularization, but it ignores a key property of images, that nearby pixels are more strongly correlated than distant ones. And modern computer vision approaches exploit this property, and information can be merged at later stages. I've already said all of this. And this now talks about a neural network performing 1D convolution. The input is x0, x1, x2, x3, x4, x5, x6, x7, x8. This is the input that is being applied. And we are applying a kernel which is of the form of zeros, W1, W0, zeros. Okay, that's the kernel GT. This is FT, this is GT. And this is as if we are shifting W0, W1, W0, W1, W0, W1, W0, W1, W0, W1. So you see W0, W1, W0, W1, W0, W1. So we are repeating these weights, we say, repeating these weights. And use that to produce some values here, to which we applied a sigmoid. So basically we are saying y naught is equal to sigmoid of W naught X naught. W naught is a vector. In this case, it captures this W and W naught in them. And it is W naught X naught plus W1 X1 minus B. So that is what Y naught is. And similarly, Y1 is this quantity. I guess this W and this W should have been the same. This is lowercase, is uppercase. So these are uppercase, they're shown as uppercase, which is the same values here. So we can also write these equations in terms of elements of a general 8 by 8 matrix W as what we are doing here is we are taking the X vector, converting it into a Y vector by multiplying by this W vector whose values are W naughts along the diagonal and W1s over here. And so this is, instead of showing it like a neural network like this, we can simply say all it is doing is multiplying the X vector by the W matrix to get us the W matrix. After that, we need to apply the sigmoid also to get the values of the Y's, right? So this is kind of a diagrammatic representation of what goes on in a one-dimensional input and then convolution with a kernel. So we are using convolution. But what is interesting about it here is that the weights are all mostly zeros over here. These are also zeros. So only values over here are defined by the kernel. So it's kind of a reduced number of computations. Normally, we would have to take for every input, everything coming in into that. So we're saying don't bother with this particular value y not being dependent on x2, x3, x4. Only it depends on x0, x1. So that is where the local receptive field comes into play and not the entire scheme of things, which makes it easier because so many multiplications are avoided, and that is essentially captured by this matrix, which has got all these zeros. And so neural networks efficiency is improved by using this kind of a matrix when you go from one layer to the other. And we say, well, what you're doing is convolution. And that is a convolutional neural network is what you've got because you got a matrix here with tons of zeros. So all of that discussion of biology and all that gets boiled down to mathematics as a simplified weight matrix that we're using. Here is another example of we say sparse connectivity. That's an obvious point. This is an interesting picture. Zebra, and when you close up zebra, it looks like that. In an image of the zebra, it looks like this here, right? So these whites have low values and the blacks have high values here. So this is a kind of image you have. Convolutional neural network would be trying to do things like detecting the edges and things like that in the zebra. Um, so we have input image may have millions of pixels, right? This is a maybe high resolution image, but we can detect edges with kernels of hundreds of pixels. So the kernel may be like, this is a millions of pixels image. The kernel is hundreds of pixels. And we can apply that and detect all the edges. And so tremendous efficiency gained by using a convolutional. So another way of looking at convolutional is traditional neural network layers use matrix multiplication by a matrix of parameters with a separate parameter describing the interaction between each input unit, each output. So we have x1, x2, x3, x4, x5. We're saying, okay, let's look at x3. X3 influences all the output values. The outputs are all S1, S2, S3, S4, S5. So this one influences S1, S2, S3, S4, S5. So that is a conventional layer of a feed-forward network. Whereas a convolutional network layer has sparse interaction. And so because of all the zeros we use in the matrix, it says this one is going to influence only these three. So this X3 influences only these three. Okay, similarly, every one of them gets influenced by only a small number here. So this one influences, this is looking at what influences what in the downstream. Upstream is another interaction. Okay, we just saw this. So sparsity of CNN versus full connectivity. So this is sparsity viewed from below. So instead of this influencing everything, and this only influences few, sparsity viewed from above, if you ask the question, how did you get this value over here? It says, well, it depends on only these three values. As opposed to in a full connectivity, that pixel is influenced by all of the pixels in the input. So you can see that this is called sparsity. It's as if these were the only connections instead of all these others. We don't need these diagrams and all that. All we need is know what the matrix is. And so, but that is the essential effect is we are using sparse connections in the neural network. All right. So pooling is another special kind of operation where we go from one layer to the next, called a pooling layer. A key aspect of convolutional neural networks are pooling layers, typically applied after the convolutional layer. So you do one layer of convolution, and a pooling function replaces the output of the net at a certain location with the summary statistic of the nearby inputs. It says, instead of having a full high resolution input, reduce it by pooling the example, by pooling the values as shown in the example on the next slide. So it says, supposing you had an input image that looks like this: 1, 1, 2, 4, 5, 6, 7, 8, 3, 2, 1, 0, 1, 2, 3, 4. This says pool all the values. It's a pooling by 2 filter and stride of 1. So instead of using 1156, I replace it by, let's say, the max pool. The max value is 6. Similarly, 2478, the max value is 8. 3212, the max value is 3, and 1034, max value is 4. So we call this, we replace this layer with this layer. Of course, we may have to do this by stride of 1 and stride of 2. Here we are using stride of 2. So we didn't use stride of 1. Stride of 1 would have given us a larger output. Then we could pad and get the same size as this one too. And so popular pooling function, the max pooling operation, which reports the maximum output within a rectangular neighborhood, average of a rectangular neighborhood, L2. Oh, okay, so we can use different kinds. We can use, this is called max pool. We can also use the average value of this 1156, or we can use the L2 norm of a rectangular neighborhood. We can say, well, that's a vector of 1156. You can compute the length of that vector from the origin, and which involves squaring them and adding them and taking the square root, Euclidean distance type of thing. That's called L2 norm. And weighted average based on the distance from the central pixel. So all kinds of clever ideas will be used. Max pool seems to be the popular approach with CNNs. So why do we use pooling? Why do we want to replace our high resolution image with something else? It provides a fixed size output matrix, which typically is required for classification. We can reduce the size by using a stride and so on that is appropriate. And say, instead of using a 4 by 4, we need a 2 by 2 or something like that. So with 1,000 filters and max pooling to each, we get a 1,000 dimensional output regardless of the size of the filters or size of the input. So one can be clever about this. This allows you to use variable size sentences, variable size filters, and always get the same output dimensions to feed into a classifier. Okay, that can be used for NLP also, where you can go from one layer to the next layer by using max pooling and get standard size outputs. Pooling also provides basic invariance to translating, shifting, and rotation. So not only does the convolutional network involved using some set of kernel values, whereas pooling is simply reducing the resolution to get a lower resolution. And that also provides basic invariance to translating, shifting, and rotation. When pooling over a region, output will stay approximately the same even if shift rotate by a few pixels, because max operation will pick out the same value. And here's an example. How does pooling introduce variance? This example tries to do that. So we have the detector stage. Okay, so we have values, some outputs of some nonlinearities produce 0.1, 1, 0.2, 0.1 over here. Pooling is saying outputs of max pooling. It says every one of these is connected to three value, like one, this one is connected to 0.1, 1, and 0.2. Max pooling says take the three values and replace the highest value and obtain the highest value. This is 1. Let's say this was also 1 here, highest between 0.1 and 1. And highest between 1.2 and 0.1 is 1. Highest between 0.2 and 0.1 is 0.2. So this is the max pool output. Supposing I took this input and I moved it by one value to the right. So from the left comes in some value, let's say that was 0.3, it wasn't seen before, that has come in a shift. And 0.1 has moved here, 1 has moved over here, 0.2 has moved here, and 0.1 has been shifted out. So now we apply pooling. So this value becomes 0.3, this one becomes 1, this one becomes 1, this one becomes 1. So now let us observe these two cases. In the first case, we had the input at the detector stage like this, and then the next one is slightly translated version. And now we can look at how did the output change. The output has, this 1 and 1 has remained the same. This one has gone from 1 to 0.2, this one has gone 0.3 to 1. So we can say this, say but the thing is every input value got changed, 0.1 to 0.3, 1 to 0.1, 0.2 to 1, and 0.1 to 0.2. But at the output, only two values change and two values remain the same. So we can say every input value is changed, but only half the values of the output have changed, because max pooling units are only sensitive to the maximum value in a neighborhood, not exact value. So we are brought in some level of invariance to the translation, so it's not so subjected to a minor shift in the data. So that gives you some idea of why does a neural network, a convolutional neural network, have a convolutional layer as well as a pooling layer, which a pooling layer helps invariance. So a convolutional network architecture, here you have some image here, and we have used three different kernels. So one could be an edge detector, blurring, or left edge, right edge, so on. So this image has become three images, three. And we have applied, so this, the value you are getting here is dependent only in the small layer here. That's the convolution operation. It ignores everything else. Just that is determining this. And then we have a pooling layer. We just discussed what is pooling. It says take these values here and take a representative of that. So we pool those values. So again, we have three layers. Maybe they become smaller because we haven't done the padding and all that. So we get this. And then it says apply another convolution to this. Apply another pooling to it. So this is what a typical deep learning architecture looks like. We go from input to convolutions to pooling to convolutions to pooling. So they put several layers. What we are essentially doing is we're allowing local images to be integrated together as we create more layers. So it is capturing the relationship between the left bottom part and the upper bottom part, if there is any kind of relationship. So that is all being captured here. In a typical neural network, deep learning neural network, when we have finished all this processing, obtaining the features, you can think of this as feature values, like the basis function values. So you see, this whole thing you can think of as computing the basis functions for the final operation of classification. So all of this was to extract the features, phi. This phi is being done. It's obtained from the data, except of course we had to prescribe the kernels for these. That kind of drives as to what kind of operations you're doing. And that is, when we do convolution, again, this has expanded the number of channels, they call it. So that's because we might be using different kernels. It's become larger, but the number of pooling has remained the same. And now we take the values provided by these pooling operations. I guess it's become increased here also. I don't know how exactly it was done, but we get these are the features, fully connected. Now we are using a fully connected layer. What it means is, while these were all sparse connections here, we are now using a standard neural network where we're using a standard matrix multiplication, and then standard matrix multiplication, and then doing the softmax, which is saying dog and cat and boat and bird, and this is saying boat is 0.94 and bird and cat are low, which means this is detected that this is the image of a boat, right? So in a way, this tells us what is the convolutional neural network architecture. Um, this again shows the same idea. There's nothing new here. Input image, and it's showing the overlap when we go from the input image to the convolutional layer image. It gives an example. And then we take 10 by 10 units here, and then becomes 5 by 5 units in the subsampling layer or the pooling layer. It shows you the process of convolution and subsampling. All right, my slide was made, like 10 years ago or something, where we didn't use the word pooling that much. We used to call it subsampling. Today, nobody calls it as a subsampling layer. They call it a pooling layer. Two layers of convolution and subsampling. Right? Input has become 3 convolutional outputs, and then these are the sigmoids are being applied. And then we apply a convolution again here, and then sigmoids, and then we get right. So the C3 level. Okay, let's see. Rasterized pixel. Okay, that's what this says. It says this is a rasterized, so it becomes a vector. So this has become a vector. This has become a vector. The hierarchy then produces S4 in a manner analogous to S2. Finally, rasterized pixel values are presented as a vector to a conventional neural network. NN is a conventional neural network. So this is the kind of architecture of a feed-forward neural network, and also referred to as a CNN, convolutional neural network. Yeah, I got some other examples here. Input layer, 4 feature maps. So 4 kernels. And then this is subsampling layer, convolutional layer, subsampling layer, fully connected multi-layer perceptron. So that's the standard design when we get to the last part, saying everything gets connected to everything here with a hidden layer, one hidden layer, and an output layer. So we say by weight sharing, invariance to small transformations of translation rotation achieved. That's kind of regularization. And it's similar to biological networks, local receptive fields, and a smart way of reducing dimensionality before applying a full neural network. So full neural network is over here. So this is, we are computing the appropriate features. So that is what we get by these neural networks that are automatically computing features phi. Oh, it's repeating itself. Okay. Um, maybe I have slides here duplicated. That might have happened. All right. What about backprop? So we saw Backprop was a topic earlier on about how do you find the weights, and we have to compute derivatives along each link and multiply all the derivatives as called for by the chain rule. So we get the derivative at the input from the output, and then we can use that to update the previous values of the weights. So what is so special about it? So we can do the same thing with a convolutional neural network. 5 by 5 input, 2 by 2 kernel, convolution, 4 by 4 feature map, 2 by 2 max pool, 2 by 2 feature map. And then we have this non-linearity being applied here, sigmoid or ReLU or whatever. And then that creates values here, H1 and H2. And we're using a conventional neural network, O1 and O2 are produced here to produce values 1 or 0, right? Two-class classification, right? So after complete forward pass and partial backward, okay, this is now trying to illustrate the idea of backprop. So we have an image here, 5 by 5 input with these values. The kernel was these values. For this one kernel, right? We saw examples of multiple kernels. This is only one kernel here. And so we get a new output here. And then we are doing max pooling here. These 4 values get replaced by 1, I suppose. This is 0.31 in this 4 square here. And we apply sigmoids to these values like that here. We get these values. And then these sigmoids are multiplied by a set of weights here to get a delta value here, which are used for the output. Assume we have already completed forward pass and computed delta H1. So we have some set of values here. And so it says delta 1, 1. So what are the values that are produced? Output here, delta 1, 2, delta 2, 1, delta 2, 2. And we are then propagate delta to the 4 by 4 layer, right? Set all the values, filtered out max pooling to 0, okay? So it's giving you some detail about how these values are evaluated, and it's giving you an exact calculation of how all these values are obtained, okay? So you may want to look at that carefully. I don't have much more on that. It seems to be an effort to say what is the nature of backprop for a simple case. So there's really nothing no different here than the other backprop. We are specifically dealing with a convolutional neural network involving max pooling. And yeah, I guess the lesson to be learned here is max pooling layer or a convolutional layer are like any other layer in a deep network. And they are learned, the weights going from each to the next are being learned using standard backprop. There's nothing special because it's also matrix multiplication. So advantages of convolutional neural network: minimize computation compared to a regular neural network. Tons of zeros here. Convolution simplifies computation a great extent without losing the essence of the data. They're great at handling image classification, and they use the same knowledge across all image locations. It's saying it is using the same weights across the entire image. And so it is computing the same kind of thing throughout. And at a later stage, they get related. Okay, that seems to be all I have on this topic of convolutional neural networks, right? So I'm going to close this. Are there any questions on CNNs? Okay, all right. So let me close this.